Good morning, everyone, and thanks to the organizer for having invited me. And I must apologize. Yes, I realized that my passport had expired much too late to be able to do anything to join you. So you'll have to bear with me from a distance. So I'd like to present rapidly some, things about Tapenade, and I tried to contrast with the little I know about Enzyme. So in a nutshell, the AD model of Tapenade is source-to-source AD. So that's one of the starting and main differences, of course, because our goal is to start from a source in Fortran or C, and hopefully in more languages, and present the user with another source that does differentiation. The two modes that we are providing are the tangent mode of AD and the adjoint mode or gradient mode. And visibly, adjoint or gradient are the most interesting, difficult mode, and it's basically our focus. Both can be multi-directional. That's called vector mode, so you can run them in several directions at the time. And inside adjoint AD, the most difficult operation is the data flow reversal, which is providing the intermediate values of the computation in reverse order. And we do that with a stack. So this is called the store all strategy. And we implement the TBR analysis that reduces a little the size of the number of variables you need to store. But to definitely reduce it and keep it manageable on large codes, we need checkpointing. So we provide checkpointing on subroutine calls and also on any set of code fragments that the user may designate. So there is support for fine-tuning of this checkpointing, which is the essential optimization that you can apply to the adjoint code. That is, the user can select some calls that must be checkpointed, some others that must not, and some fragments of code that must be checkpointed as well. There is also support for binomial checkpointing. Actually, it's built in. Also built in is the strategy for fixed point loops, the two phases method from Christensen. There is support for efficient adjoint of linear solvers and of this kind of loops, which is quite frequent, loops where there is no data, no dependency carried by the loop carried dependency. The input languages that we can deal with are Fortran, more or less less than 2003, and C, less than C99. But basically, the most frequent constructs are there. Our hope at the beginning was to be agnostic to the language of the application we're working on. So there is a single input language in reality, which we call IL for imperative language, which is abstract. It has no syntax, but it has tree. It has operators. And so far, it's the union of Fortran and C, plus partial support for constructs from MPI, OpenMP, and CUDA. IL itself is an AST. It's more on the source side. If you see what the AST that Clang, for example, provides, it has two aspects. They say there is a more source side and a more compiler side. Our AST is more on the source side. It can be extended further. Of course, we have always the hope of extending it to larger set of languages. Why not C++? Why not Julia? But this has never been completed so far because it takes time and manpower, which we are lacking. Oh yeah, this slide is, I can't avoid it, but I must be quick. So it's the place where I boast. So Tapenade is open source. It has an MIT license. You can also use it from a web server. There are a number of academic users. There are a number of industrial users. Some of them did pay a license in the past when it was not open source. Now it is. The performance of Tapenade in CPU and memory is generally considered good. In general, the slowdown of the tangent code with respect to the primal code is about 2, and the adjoint or gradient slowdown is about 7. Well, it may change, of course, according to the example. It's often used as a reference. I saw several times presentations where people use Tapenade as the reference for their timings, which is always pleasant to see. It is 150,000 lines of Java and 20% year of development started in 99. This is a part of our non-regression tests. These are real codes, some of them small, some of them larger. And you see the first column in red is the slowdown of the tangent code with respect to the primal, the slowdown of the adjoint in the next red column, and the consumption in memory for the data flow reversal on the third column. Yeah, so if you look at the last but one line, for example, it's the largest example on this set. It's the MIT GCM in one configuration, of course. You see that I think we can be pretty happy with the slowdowns, which are comparable with another reference tool, which is called TAF. The architecture of the tool now is probably what you want to hear about more. So it's source to source, like I said. So the story starts here on the top left, where we have source files that are parsed, and each of them produce a tree in this IL language, which is the actual input of Tapenade. From there, we build the internal representation, which is basically a call graph, and each node of the call graph is itself a flow graph for each subroutine. And well, that's about all. So on the internal representation, first, we run a number of data flow analysis. Some are very classical in out pointer destinations, for example, points to. Some are specific to AD, such as activity analysis, TBR, and a few others. All these are attached to the internal representation, which is then ready to go through differentiation, which builds another internal representation for the differentiated code. And then the rest is very easy. Well, not so easy, but it's very logical. From the differentiated internal representation, we go up to a differentiated IL tree, and then it is printed as a C or Fortran code. What else? Yeah, still about data flow analysis. What we are proud of about this data flow analysis is that they are global. They run on the complete code. So they are context sensitive for the calls, and they are flow sensitive, of course. They handle the flow in the flow graph. The granularity of the data flow is, I think, reasonable. Arrays are considered as atomic. There is no sense in trying to distinguish the in-out status, for example, of each individual element of an array. So it will be a collective information. On the other hand, each field of a record is analyzed separately from the other fields. Like I said, yes, it's run on the call graph and the flow graph structures. Here's the list of, well, it's partial list, but of the analysis. In red are the analysis that are specific to AD. Activity detects what variables need a derivative or will have a non-trivial and useful derivative. Diff5 is the original code instructions that are needed to compute these derivatives. Otherwise, you can take them out. TBR is about variables whose intermediate values need not be stored because they will not be used during the reverse differentiation. Um, Basically, all these AD-specific analyses are specializations of partial evaluation and splicing. So you may argue that there's no point in implementing them. However, well, if the compiler does it for you. However, I believe it is still useful because they are specific to the structure of the differentiated code. These analyses know about the structures. They know there will be a forward sweep followed by a backward sweep, and they know there is a sort of first in, last out correspondence between points in the forward sweep and points in the backward sweep. And all this makes the analysis much more powerful than a general purpose analysis on the whole lot of differentiated code. At least that's what I claim. Yeah, and if you want to have a memory efficient checkpointing scheme, you really need to have an accurate AD specific analysis to get the TBR information and also to have checkpointing sets, the set of variables that you need to store before checkpointing a call as small as possible. So there are questions that I may ask you in a sense. Is it really possible that only a post-AD general compiler optimization perform like that as well? And I doubt it's likely, but yeah. Yeah. And also, does Enzyme rely only on the general data flow analysis, which is provided by the surrounding compiler, LLVM, or does Enzyme have to implement its own homemade specific analysis? And these homemade analysis, do you think you need to have them local on some window of the LLVM code, or do you think they need to be global and they need to extract information from distant places? Well, these are the questions I would ask. Still a little publicity about these data flow analysis to show you how profitable they might be. On the left is, well, of course, you please don't look at the details. It's just a blink of an eye. On the left is the code that you get in the reverse sweep of an adjoint code. If you do not apply any data flow analysis, then if you run diff liveness analysis, taking away primal code, which is not necessary for the derivatives, you get fewer lines. Then if you run the TBR, you get fewer push and pops. And later, if you replace some of the TBR storage by recomputation, you get even fewer push and pops. So the resulting code is hopefully more efficient and also smaller. Yeah. There are a couple of other choices I wanted to point out. We chose not to care too much about the qualities of the source. We don't want really to optimize the source. You know, it's a little like people sometimes call it garbage in, garbage out. Well, of course, it's not garbage at all. But when there is some little glitch in the source code, we don't really care about it. Where our only goal is to not introduce new inefficiencies. So we have something like common subexpression elimination, but I would rather call it common subexpression avoidance. We don't want to introduce through AD new common subexpressions. And already it gives a little difference, you see. This is a naive adjoint when you don't have common subexpression avoidance. And this is the resulting code if you do. Again, I think it's interesting. Also, we are stuck to source AD. We really like it. But on the other hand, it seems that speed of AD is not our speed of AD itself. The differentiating process is not our strong point. For example, it takes 5 minutes to run Tapenade on the GCM example, and it's probably hopeless for the Tapenade AD model to run in JIT. Well, I don't know. Many of our users appreciate seeing the differentiated program as another source. They like to play with it. for education as well, it's also useful. And for debugging, well, yes, because there are bugs, plenty, sorry. So debugging is, of course, never good enough, but we provide it at the level of the differentiated source, which helps you focusing on the faulty place. As a final outlook at the end of my presentation, I'd like to well, tell you of some limitations that maybe we can lift someday. Of course, we have this limit of the new languages. It's hard to provide a new parser and a new front end for new languages for Tapenade. You are probably much better off at the level of LLVM, you lucky guys. And also, yeah, if we want to do something about object-oriented languages, being a little too high, too high level compared to LLVM leads to plenty of difficult questions about data flow analysis of really object code. So there is this question of dynamic memory. If you use dynamic memory, things become complicated because if you free some memory, then during the gradient, you need to reallocate it and the address will not be the same. So every pointer that you have stored becomes meaningless. That's even worse when you have garbage collection in the application language. So the only solution I can think of is to use a pseudo address that you attach to each allocation point, each malloc at runtime. Well, it makes a source transformed gradient rather complicated to read using that. It works, but it's very hard. Of course, I should have said that first. The immediate solution that one can think of is to say, okay, let's not free memory, but this doesn't work because it doesn't scale. Memory will explode very quickly. About parallel codes, there are also a few limitations. The good point to begin with is that we can work on OpenAD, OpenMP, and CUDA using the same primitives inside IL, which is good. There is this notion that adjoint turns reads into increments and vice versa, which is a nice duality. But this is nice only as long as increments are considered atomic, which is not the case in general. And if you use atomic pragmas, it will become very, very slow. And we do not handle some parallel constructs, such as the one-sided communication. So Michel Shannon has done something interesting about that, but we don't. This is my last slide, I think. It's about the relation between, or comparison between, source transformation AD and what is used to call operator overloading AD, but I would rather call it trace-based AD. The main difference between the two being that in trace-based AD, you store every intermediate value and you store every operation of the primal code onto a tape. On the other hand, with source transformation, you tape only the intermediate values and the rest is taken care of by a new code. So if you do overloading AD, you have pseudo addresses for free, which is good, but you have unrolled all the code and loops create a lot and a lot of space on the tape. That's not so good. So it would be interesting to investigate blends between the two. Source transformation definitely should use the pseudo address and takes and would benefit from the experience of overloading AD. And conversely, overloading AD could use some source transformation methods to reduce the number of the pseudo address that they use because they have one per line, and to re-roll what's been unrolled in the trace. And with that, I think I thank you for your attention. I'm ready to answer your questions if you wish.
Come closer because only this mic works, or be really, really loud. Billy, do you want to answer questions that Laurent had?
Yeah, I can come up here for a second to do so, but yeah, I can answer some of the questions on the analyses that you had earlier. If you don't mind just flipping back to that slide real quick. It hypothetically is on. Yeah, I can do that.
Was it? Where was it? Here.
So I'll go sort of like in a mixed combinations of orders. So on the second question, we actually do both. So we both borrow existing analyses in LLVM. Some of the most impactful ones that we found include, generic data analysis, but in particular like alias analysis and a bunch of other sort of mechanisms like that. We then also extend these structures to add new sort of AD-specific analyses. So we do have an activity analysis. We do have we give it a slightly different name from to-be recorded analysis. We call it, a differential use analysis and sort of split it off from a different sort of subpart, which we do like a min cut to do sort of like caching style analysis. But these sort of, we have the AD-specific ones and we have the sort of LVM general ones that feed into each other and get some mutual benefits. On sort of question 3 on the local versus global sort of editions of these analyses, we actually, again, we have both. The way that we do this, because we need to be able to handle both a generic function, which might be a captured piece, and we want to handle indirect function calls, like say for virtual functions, that might not have the global state outside of it. But of course, if we have sort of the global state of all these pieces, we want to use that information. So most of these analyses have modes that allow you to have both interprocedural as well as sort of function local variations of it. So what we do is we sort of seed the analysis with the surrounding outside context and then run sort of pieces. And sometimes, depending on what that context is, we can go back and update that. The one that is most commonly used in that sort of realm is something called type analysis, which we use to deduce is, are you storing an integer, are you storing a float? Because especially if you have a subfunction, which is a pointer plus offset 1, that you want to see the surrounding outside scope as well, since that inner function might not tell you a lot about what's happening. Now sort of circling back up to the question 1, sort of variation of do we do some of these general sort of slicing and other sort of pieces? Again, we actually build off of these analyses to do some of these pieces. In particular, as an example, that type analysis that I mentioned earlier is particularly useful for being able to say, these subparts of an array, because we see that only at this region you're loading what otherwise might be an inactive value, so we can deduce from those pieces that we don't need to handle it in the same way as it might be if it was a active floating point value and the likes of that. So we have a sort of slightly more, we have a slightly general sort of version of it, but we also have a similar current assumption where we look at the entire pointer, entire array at large as being active or inactive, and then the individual get element pointers, which is the LVM speak for sort of offsets into that might be loaded or stored, have additional information as to that individual location, might have some extra pieces alongside it from the individual type loaded or stored, but the sort of more general fallback is to consider it as an entire array at once. If that sort of answers some of those individual specific questions.
Okay, thank you, Billy.
Any questions for Laurent? Well, I have a kind of, I have my mic. So I have a kind of question. So you have this imperative language, which to me is an IR similarly to what LLVM IR is. Just you don't want to have like parser and printer for that. Mm-hmm. What part of that language do you think is most helpful for doing AD? Because LLVM is really low level. What you see is control flow with branches and like scalar additions. I suppose you're at a higher level. So what would be the most interesting thing to have if you wanted to add it to LLVM, for example?
I think one interesting point to have is to keep a correspondence with the actual source, to be able to talk to the end user in terms of the actual source, to have these data flow analysis tell each and every message that they or warning that they want to tell in terms of the original source. So I guess you have that in Enzyme. If some data flow information is about some LLVM variable, you know, the ones that are named with an underscore or sharp sign, or I don't remember precisely. It would be interesting to translate these into the original variables of the source.
Okay, so what we have is sort of location information. So it says this part of LLVM comes from this line in the source code. But
that's already very good.
Yeah, but there is no mapping to a variable, for example.
Yeah,
so it just says, well, it's line 13, column 55. That's all it can give you.
Yeah, that's good. What else? I think it's good to be able to add each individual construct that a new language or a new version of a language provides. So, of course, it's the same question for LLVM. And so I suppose, yes, LLVM will increase and enlarge as soon as new constructs appear in the target languages. So
what happens usually with LLVMs, they try to translate those. So like if somebody adds, I don't know, a multi-for loop, it will still go to branches. So
yes, we do that as well, of course. As soon as we can find that some new construct is indeed a shortcut of existing constructs, we keep the existing ones. It's we agree on that, definitely. Yeah.
Okay.
Yeah, question?
Thank you. Any other questions? Comments? No? No? Okay, can you please come here and get a mic?
So, okay.
Yeah, so he can see you.
Hi, Laurent. So I'm probably the least knowledgeable about AD under the hood specifics, but one of the big users of AD. And I wanted to sort of bring up this point that Laurent made before, and maybe also to recognize the adjointed code, right? Or at least in the source-to-source transformation, just wanted to highlight the importance for some of the users. And we're coming here from sort of the climate or weather modeling community. And in many of the large centers, if you go, for example, to one of the biggest centers in Europe, the ECMWF, or some of these centers in the US, they will not use AD, right? And the reason they won't use AD, they don't trust it, right? So there's one major US ocean modeling effort. They basically took a paper that some of you will know, Recipe of Adjoint Code Construction, and they say, well, we basically took that paper and then we wrote our adjoint code, right? ECMWF have an adjoint code for their numerical weather prediction. And again, it's all handwritten because they don't trust AD. And so the point that Laurent made before is one that I just wanted to basically emphasize to this community again, is that the ability to sometimes to derive exact adjoint code and then after the fact look at trying to understand it and potentially simplify it by shortcutting certain things is one that is important for users and may sometimes make or break people's willingness to use AD or not, right? So I just wanted to mention and highlight this again from really an application perspective. Thank you.
Thank you.
Thank you. Thank you. May I, I'm a slow thinker, and I'm thinking of a reply to the previous question. What would be very interesting to have? I think something we appreciate is in the data flow structure, for example, well, not the control flow structure that we have. It's to really keep as much as possible the structure of the loops and the structure of the control and reject as much as possible go-tos and jumps. And if you have something that is a little too much like an assembly language, you have this risk. And if you do, because these structures that are present in the control flow graph are extremely useful to have an efficient agent. Of course, you will detect this way the parallel loops, you will detect the fixed point loops, you will, or well, not really detect, but you will take advantage of. And the analysis themselves, for example, can be much more efficient when they know that, for example, each and every cell of an array is overwritten during the loop. And so you know that the array is completely killed. So all these things are, for us, much easier to perform on a real flow graph rather than on something that has a little bit of too many threads and jumps.
Too many go-tos.
Yeah. Okay. Sorry for being long.
Sure. It's kind of the answer I was looking for. That's why I was fishing a bit with like multi-for loops. So I think we are running out of time. So if there are further questions, I may be able to direct them to Laurent, or if Laurent is comfortable with that, we can share his email so you can ask questions further.
Of course. No problem.
So let's thank Laurent again for his presentation.
Thank you.
I will